Hi everyone, welcome to the first week of Internet-Computer Protocol journey. This week we are going to have a basic overview of the Internet-Computer Protocol, and then we are going to dig a little bit deeper on the architecture and the inner workings of this technology. After having this understanding on the Internet-Computer Protocol, we are going to set up our developer environment so that we can start developing our smart contracts next week. So, before further ado, let's get started. Hi everyone, in this video we are going to have an overview of Internet-Computer Protocol and its core difference with other blockchains. In this video we are going to talk about the brief history and background of the Internet-Computer Protocol. Then we are going to continue with the purpose and vision of Internet-Computer Protocol, key components in the IC ecosystem, and finally we will have our conclusion. Now, what is ICP? The Internet-Computer Protocol developed by the Dfinity Foundation. It's a revolutionary blockchain infrastructure that seeks to expand the functionality of public internet. It's officially launched in 2021 after several years of intense development. Now let's look at the purpose and vision of Internet-Computer Protocol. The primary vision of Internet Computer is to provide a limitless environment. The Internet Computer is not just another blockchain platform. It's a radical new way of building and running software on internet. Imagine if you could create any kind of application or service without worrying about servers, hosting, scalability, security, or performance. Imagine if you could deploy your code directly to the public internet and let it run forever. Imagine if you could access any data or functionality on the web with a single click. That is the primary vision of Internet Computer, to provide a limitless environment for developers and users to create and enjoy the next generation of internet services. One of the most amazing features of the Internet Computer is that it allows you to run your software directly on the public internet without needing any central infrastructure or services. This means you don't have to rely on third-party providers like Amazon, Google, or Facebook to host your application or store your data. You don't have to worry about censorship, downtime, hacking, or fees. You don't have to compromise on your privacy or security. You can simply write your code and deploy it to the Internet Computer Network, which is composed of thousands of independent nodes that work together to provide a seamless and unstoppable computing environment. Now, let's look at the key components of the Internet Computer ecosystem. First, we have the data centers. Data centers are physical locations that host the hardware and software components of Internet Computer Network. They are composed of servers, storage devices, routers, switches, and other equipment that provide computing power, storage capacity, and network connectivity. Next, we have nodes and subnets. Nodes are individual computers that run the Internet Computer Protocol and execute the software deployed on the network. Nodes are grouped into subnets, which are collections of nodes that work together to provide a specific service or functionality. Subnets can communicate with each other through message passing and can scale up or down depending on the demand. Subnets are also responsible for ensuring the security and reliability of the network by validating transactions and reaching consensus. Here, it's important to mention that node providers are not equal to data centers. Node providers host their nodes within data centers, but the data centers themselves don't usually run nodes, they just rent out rack space to the node providers. There can be multiple different node providers within one data center. Now, let's look at the network nervous system. The network nervous system, which can also be called as NNS, is a decentralized governance system that controls and manages the Internet Computer Network. The NNS is composed of neurons. Neurons can propose, vote on, and execute proposals that affect various aspects of the network, such as upgrading the protocol, creating new subnets, allocating resources, setting fees, and more. The NNS is designed to be adaptive, responsive, and transparent, allowing the network to evolve and improve over time. Next, we have chain key technology. The correct operation of subnets and inter-subnet communication relies on a suite of novel cryptographic protocols, collectively referred as chain key cryptography. Chain key cryptography makes it possible for subnets to authenticate responses to user requests, the subnet state, and inter-subnet messages in a completely decentralized way. And finally, we have canisters. Canisters are the basic unit of software deployment and execution on the Internet Computer Network. Canisters are self-contained bundles of code, data, and memory that run on subnets and communicate with each other through messages. Canisters can implement any kind of functionality such as web services, smart contracts, decentralized applications, or user interfaces. Canisters are scalable, secure, and autonomous, meaning they can adjust their resource consumption, protect themselves from malicious attacks, and manage their own life cycles. These components work together to create a seamless and unstoppable computing environment that can host any software or service on the public internet. The Internet Computer Network aims to provide a limitless platform for both developers and users to create and enjoy the next generation of internet services. As a conclusion, the Internet Computer, an innovative blockchain network launched by the Dfinity Foundation in May 2021, aspires to be a scalable, open, and secure world computer. It hosts programs and data as smart contracts, known as canisters, on a network of subnets, with each canister having its own isolated data storage and communicating seamlessly with others across the network. The Internet Computer Protocol at the core of the network ensures fault tolerance and scalability. Thank you very much for listening to me on this video, and I will see you on our next one. Hi everyone, in our last video we had a quick overview of the Internet Computer Protocol, and in this video we are going to have an introduction to the concepts where we dig deeper. So let's see what is waiting for us. First, we are going to talk about the canisters, which is followed by the nodes and subnets. Then, we are going to talk about chain key cryptography. Next, we have the database versus blockchain comparison. And finally, as usual, we will have our conclusion. So, what are canisters? Canisters are the fundamental building blocks of Internet Computer, acting as both the storage units and computational entities. When we refer to the canisters as the fundamental building blocks of the Internet Computer, we mean that they are the core units that make up its infrastructure. They serve dual purposes. They are both the storage units and the computational entities. This means that they not only hold data, but also have capabilities to perform computations, which is a unique feature that differentiates the Internet Computer from traditional blockchains. Canisters are autonomous, scalable, interactable, implying that they operate independently, can adjust their capacity based on demand, and can interact with other canisters or external entities. They run WebAssembly bytecode, which is a binary instruction format that allows them to execute code at near-native speed. Housing both the data and the code implies that canisters encapsulate the state of functionality of a software service, which streamlines the development process on the Internet Computer. Now, let's look at the advantages of canisters over smart contracts. Canisters can run at web speed, meaning they can produce blocks and finalize transactions in milliseconds and without compromising security or decentralization. Canisters can scale up or down depending on the demand, meaning they can adjust their resource consumption and performance dynamically. Canisters can communicate with each other and with other blockchains through message passing, meaning they can interoperate seamless and efficiently. Canisters can persist their state across upgrades and reboots, meaning they can maintain their data and functionality without interruption. Now, let's look at the inter-canister communication, which is a crucial part of the Internet Computer Protocol. The Internet Computer's multi-subnet architecture allows canisters on different subnets to communicate with each other seamlessly, similar to traditional microservices architecture, fully on-chain, which is very important to have a full functional replacement for traditional systems. Canisters communicate via asynchronous messages, allowing the Internet Computer to scale by adding more subnets. Since we have a system here which is not fixed, which can grow on demand, this becomes a very important feature. Now let's look at a specific canister, which is the management canister in Internet Computer. This is not an actual canister with isolated state and WebAssembly code. Management canister address with the specific address known as empty blob. Canisters can interact with the Internet Computer management canister via inter-canister calls. So let's look at the restrictions of the management canister. Our first restriction is that most methods only permit the controllers to call them. Calls to row, rand, and deposit cycles are never accepted as ingress messages. Now that we know about the canisters and management canister, let's look at the nodes. So, nodes are the machines that running the core Internet Computer Protocol. When we refer to nodes, we are talking about individual computers that participate in the Internet Computer Network. Each of these computers runs the core Internet Computer Protocol. This protocol governs how nodes communicate and interact with one another. So it actually sets the rules of the game, so to speak. Just like how in a game of chess, all players must follow the same rules for how pieces move, in the Internet Computer Network, all nodes follow the same protocol for how they send, receive, and process information. This uniform adherence to the same protocol across all nodes helps to ensure the security and consistency of the network. Nodes are deployed in globally distributed data centers. The nodes we just talked about aren't all gathered together in one physical location. Instead, they are spread out across multiple data centers around the world. This is what we mean by globally distributed. These data centers can be thought as a large warehouse filled with servers located in various countries and regions. By distributing the nodes in this way, the Internet Computer can provide a number of benefits. For instance, it enhances the resilience of the network because a problem at one data center won't take down the entire network. It also improves the speed and performance of the network because users can connect to a node that's geographically close to them, reducing the time it takes for data to travel back and forth. So this is like a system that we are using today. If you use traditional web service provider like an Amazon, then the option that we are going to have is very similar to this one. So it's very important for Internet Computer Protocol to give this opportunity to users so that it can run on high speeds and performance as we are doing today, but on a decentralized system. Lastly, this global distribution contributes to the decentralization of the network, a key principle of blockchain technology, as it prevents any single entity or region from having too much control over the network. That being said, it is crucial to note that node providers operate their nodes within data centers, but the data centers themselves typically do not run nodes. Now, let's look at the importance of these node distribution. Firstly, it's important because no single entity should have the power to significantly disrupt the network. This principle was challenged in the Hetzner incident. Hetzner, a popular hosting service, banned Ethereum nodes. This action effectively removed a substantial portion of the Ethereum's network nodes, leading to concerns about network stability and decentralization. And as we can see, decentralization is very crucial for any blockchain, and it's the center principle of Internet Computer Protocol. Now let's look at the subnets. The multi-subnet architecture of Internet Computer allows for seamless communication between smart contracts on different subnets, enabling the Internet Computer to scale practically without limits. Each subnet operates a blockchain-based replicated state machine, making progress independently but communicating asynchronously with other subnets. The Internet Computer offers various types of subnets, each designed with specific properties that cater to different use cases. Now let's look at these subnet types. First, we have the system subnets. These subnets are reserved for canisters that are an integral part of the Internet Computer. Typically, canisters on these subnets are controlled by the NNS and they don't pay cycles. Users cannot deploy canisters on those subnets. For that, we have the application subnets. These are the default subnets that users can deploy canisters to. But if a user does not provide any specific requirements, a random application subnet is chosen as the destination to create the canister. On top of these basic types, there are also specialized types of subnets that offer certain additional properties that might be useful to decentralized applications. The first such specialized type is fiduciary, which is essentially a larger version of an application subnet. Having more nodes provides better security and guarantees to decentralized applications running on a fiduciary subnet at the expense of being more expensive in terms of cycles cost. Now, let's learn about chain key cryptography. Subnets and their communication between each other depend on a set of innovative cryptographic protocols known as chain key cryptography. This cryptographic approach enables subnets to authenticate user request responses, maintaining subnet state, and exchange messages between subnets in a fully decentralized manner. Now let's look how ICP works with chain key cryptography. First, a replica can join a subnet by starting from the most recent checkpoint or leave at any point in time. Threshold keys of the subnet are periodically reshared between the current nodes of the subnet. Membership changes and key resharing do not affect the public key of any subnet. Periodically, previous blocks are pruned from each subnet blockchain to prevent storage from growing infinitely. Now, let's look at the network nervous system, which we know from our last video again, to understand how it works with ICP and what it brings to the table. Again, NNS is an open algorithmic system governing the internet computer blockchain, which we can say it behaves as one of the world's biggest DAOs, which we call decentralized autonomous organizations. And its further functionalities are upgrading the internet computer protocol, managing software running on node machines, and subnetting blockchain to increase capacity. Now, as a conclusion, with its core components including canisters, nodes, subnets, chain key cryptography, and the network nervous system, internet computer provides a robust and scalable ecosystem. Data centers globally host nodes, which form the backbone of the internet computer's infrastructure, ensuring high availability and fault tolerance. The vision of the internet computer is to democratize the digital landscape, fostering innovation and data sovereignty. That's all for this video. Thank you very much, and I will see you on our next video where we are going to talk about internet computer architecture. Hi everyone. So far we had an overview and introduction for internet computer protocol, and we learned about many different concepts and how internet computer works on the background. And in this video we are going to dig deep on this architecture of internet computer. So what is waiting for us? First, we have the explanation of the traditional network, and then we have a comparison between the ICP and the traditional network. Then we will talk about the core ICP protocol and the architecture of the internet computer. And finally, we will have our conclusion. So let's start with the explanation of the traditional network. Here in this example, as you can see, first we have our Wi-Fi, 5G or fiber ground. On top of it, we have the internet protocol that is necessary for every action in the internet happens based on this protocol. And on top of it, we have the cloud services. And on top of the cloud services, we have the databases or web servers. And only after that, we have our websites. But even after all these structures, we need to add the firewall to keep these attackers outside of our website. So as you can see, this is actually a multi-layer and a huge architecture that we are working with in Web 2. The general idea is that Web 3 can be a better technology, but everyone thinks in general that Web 3 is much harder to develop on and use. And we will see how we are actually making a system which is a centralized system, our current usage of the internet. We are going to transform this to a decentralized system with ICP by making it even easier for the developers. Now let's continue with the ICP and traditional network comparison. So traditional network is limited scalability, lack of security, and that's why we had this firewall and every possible integration we can find on the web servers and cloud services so that we can protect our website. The dependence on centralized servers, which is the obvious problem in Web 2, inefficient resource use, and finally, lack of interoperability. On the other side, on the Internet Computer Protocol, it's high scalable. We have chain key technology, as we talked on our previous presentation, which handles the security part for us. And of course, it's a decentralized technology and it can scale up and down using the network nervous system. Now let's look at the 4-layer protocol. As you remember from the previous slides, we had a huge architecture under our traditional network. Here we have 4 different layers: peer-to-peer layer, consensus layer, message routing layer, and execution layer. The peer-to-peer layer in the Internet Computer Protocol ensures secure communication between nodes within a subnet. It allows nodes to broadcast messages or artifacts to all other nodes, guaranteeing their delivery. Internet Computer Protocol uses a consensus mechanism to agree on and order messages. It provides instant finality, high throughput, and robustness, unlike Bitcoin's probabilistic finality. Internet Computer handles the induction and routing of messages between canisters potentially across different subnets. It ensures consistent message processing across all nodes in the subnet and enables inter-subnet communication. The execution layer is the top layer of the Internet Computer Protocol, executing canister smart contract code using a WebAssembly virtual machine on each node. So, as a conclusion, the Internet Computer's architecture is powered by the Internet Computer Protocol consisting of 4 layers. These are peer-to-peer, consensus, message routing, and execution, which facilitates efficient blockchain operations. Thank you very much. That's all for this video. And in our next video, we are going to learn about our development environment. Thank you very much and see you there. Hi everyone. Now that we learn about the architecture of Internet Computer, it's time to learn about how we can set our development environment and what we'll be using for Internet Computer development. In this presentation, we are going to learn about Internet Computer Software Development Kit and how we can install it and what we get from this installment. Next, we are going to learn about the components of Internet Computer Software Development Kit, CDK and DFX, and finally we will have our conclusion. So what is IC SDK? It's a software development kit that has necessary tools for us to develop on Internet Computer. It is for creating and managing canister smart contracts on Internet Computer Protocol blockchain. Let's see how we can install Internet Computer SDK. Internet Computer Software Development Kit is designed to work directly with Linux or macOS. But if you are using Windows, you can use WSL 1 or 2, but the second one is recommended even though both of them is going to work. To install the Internet Computer SDK, we are going to use this command below. So after this installation, let's see what we are getting. The Internet Computer SDK installation script installs several components in default locations on your computer. First, we have DFX. DFX is the command line tool provided by Dfinity for developing, deploying, and managing applications on the Internet Computer. It's designed to facilitate local development and testing. Then we have Mach, which is Motoko Runtime Compiler. Motoko is a programming language that has been specifically designed for creating software to run on Internet Computer. The Mach is used to compile Motoko source code into WebAssembly, which we call WASM format, which can be executed on the Internet Computer. Then we have the replica. In the context of Internet Computer, a replica refers to an instance of the Internet Computer Protocol running on a node machine. Multiple replicas form a subnet, and they work together to process requests, maintain a shared state, and preserve the integrity and security of the system. This term, network binary, usually refers to the compiled version of the Internet Computer software that is run on the node machines. It includes the code necessary to operate the network, process requests, and maintain the blockchain. Uninstall.sh, which is self-explanatory in my opinion. This is a shell script file that is typically used to uninstall software in a Unix or Unix-like operating system. In the context of Internet Computer, it would be used to remove the installed software or tools related to Internet Computer from your system. And finally, we will have the versions. This term in a software context generally refers to the different releases of a particular software packages. Each version would have different features or improvements. In the context of Internet Computer though, it refers to the different releases of the DFX tool, the Internet Computer software, or other related tools and libraries. The IC SDK is a software development kit created by Dfinity. It's designed to help you create and manage canisters. The Canister Development Kit is a tool used by Internet Computer SDK. It gives programming languages the ability to create and manage canisters. The Internet Computer SDK comes with a number of CDKs pre-installed, such as Rust CDK, so you can start developing in your preferred language. As we can understand from here, Internet Computer Software Development Kit is the bigger box here, which includes CDKs, which are canister development kits. DFX is the command line interface for Internet Computer Software Development Kit. This is why many Internet Computer SDK commands start with DFX, like DFX new or DFX stuff. Even though we haven't seen these commands yet, we are going to see them a lot of times in our projects, I promise. And finally, as a conclusion, the Internet Computer SDK equipped with its tools such as CDK and DFX is a crucial component for developers aiming to leverage the power of Internet Computer Protocol blockchain in their applications. Its compatibility with various programming languages, its modular components, and its intuitive command line interface makes it a versatile and user-friendly platform for blockchain development. Whether you are coding in Motoko or Rust, the Internet Computer SDK is designed to meet your needs and propel your project forward, and in our case we will be using Rust and Internet Computer Software Development Kit together to create our smart contracts and decentralized applications. So thank you very much for listening to this video, and I will see you on the next video where we make our hands dirty. So thank you very much again and see you there.